Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 52. And this problem gives us a series of 3 substituted benzene rings, and it asks us to group each of these aryl halides in each of these groups in order of increasing reactivity for your nucleophilic aromatic substitution by an addition-elimination mechanism. So what we know about an arbitrary nucleophilic aromatic substitution reaction is that we have a benzene group that is going to act as our electrophile. And the reason for that is because the benzene group is going to have some electron withdrawing groups attached to it, and a good leaving group being one of the halides, and I'll just write that as X. So we have electron withdrawing groups and leaving groups. That makes this benzene electrophilic because of the electron poor nature around the benzene ring. And we're going to react this with some sort of strong nucleophile, in which that nucleophile will attack the carbon that has a leaving group and make some intermediates, which we can show here. These intermediates are now putting a full carbanion, a full negative charge, within the ring of the benzene. And now the reason that we have these electron withdrawing groups is that once we do some resonance structure, we see that if the leaving group is ortho or para to the electron withdrawing group, or another way to saying it, if the electron withdrawing group is ortho or para to the leaving group where the nucleophile will attack, then we will have stabilization of this carb anion. And the reason for that is because in the ortho or para position, which your electron withdrawing group is going to be, in the ortho and para position that the electron withdrawing group is going to be, this negative charge carb anion is going to be stabilized by the electron pulled towards this electron withdrawing group here. So this will stabilize this intermediate, and then this can go around to kick off with your leaving group here, and you will get your substitution product here. So then you'll be left with your nucleophile ortho or para to your electron withdrawing group. And so in order to rank the 3 of these compounds in terms of reactivity, well, there's a few factors we need to consider. Number 1, the increasing number of your electron withdrawing groups on your benzene ring will increase the reactivity for nucleophilic aromatic substitution, and specifically the number of electron withdrawing groups at the ortho and para position in respects to your leaving group being one of the halides will increase the reactivity for your nucleophilic aromatic substitution reaction. Number 2, increasing the number of electronegative atoms, or in this case is going to be the halides, for example, fluorine, bromine, chlorine, will increase the reactivity of your benzene derivative for your NAS reaction. So let's look at the series of 3 compounds that are in black. So here we have to consider 2 things. Number 1, the electron withdrawing group must be ortho and para. Number 2, the number of your halides. So in these 3 cases, we all have fluorine, so number of halides is all the same, and we all have 2 2 electron withdrawing groups in each situation. But now here's the difference. The benzene groups that have your electron withdrawing group at the ortho and para position, those are going to be more reactive than something that's at the meta position, for example, the second one. So this first example here that has both nitro groups at the ortho and meta position, this is going to be the most reactive right off the bat. We can see that. Now, what about the second one? Well, this second one has both nitro electron withdrawing groups at both meta positions, while this one has one para position, one meta position. So the one that has one para position will be the second most reactive, and the one that has the electron withdrawing groups at both meta positions will be the least reactive. So you see here we have one at the ortho, one at the para. That's why this is the most reactive. This one has only 1 at the para, while this one has 0 at ortho or para. So we get our ranking 1, 2, 3. So let's do the blue set here. So the blue set, we see right off the bat that this first molecule here has no electron withdrawing group. So right away, these two already are outcompete for reactivity than this one. So we can just say this is number 3 because this only has a halide but no electron withdrawing group. Now these ones have the both same halides and they have the same identity for the electron withdrawing groups, but their positions differ. This one is at the para position, this one's at the meta position. Well, because this is at the para position, we know that in this resonance structure, this carbanion is going to be located on this carbon, which is going to be stabilized by this electron withdrawing nature of this nitro group. So this is going to be more reactive than this meta substituted nitro group, where the carbanion will not be stabilized as much as if it was on the para position. So this is number 1, and this is number 2. Last but not least is this series here. So this series, we have a molecule with 2 electron withdrawing groups, both of them being nitro, 1 fluorine. Here we have an actually electron donating group being this methyl group here. 1 electron withdrawing group being this nitro, and 1 halide being chlorine. And here we have same that methyl donating, electron donating group, electron withdrawing group, and halide. So right away we know that 1 halide with 2 electron withdrawing groups is better than 1 halide with 1 electron withdrawing group and 1 electron donating group. So we can say right off the bat this is the most reactive. Now what about these two? So these two, the more electronegative atom, the more reactive it's going to be. So we know that fluorine is the most electronegative atom on the periodic table. So we know that this molecule right off the bat is going to be more reactive than this one with the chlorine. So we know that this is going to be 2 and this is going to be 3.